difficult concept to understand in DC circuit learning is that of the open circuit, and why, when we use the multimeter, we measure the full circuit voltage across that open circuit. We've been doing a lab, the series circuit, lab number 5, and the problem occurs in lab number 5, and people still can't seem to grasp why this is so. I've drawn the circuit up on the board. We've got a 9-volt voltage source and a current meter, 3.3 k ohm resistor, 470 ohm resistor, and a 10 k ohm resistor. And if you run the maths on that, and I've just got some notes here I'll have a quick look at, and you end up with 13,770 ohms of resistance total. If you use Ohm's law and divide that into 9 volts, you're going to get 653 microamps of current flowing in that normal circuit setup. And if, however, we then take out, before we do, the normal voltages derived here mathematically by multiplying the normal circuit current by the individual resistance values, so V equals I times R, 2.15 volts, 307 millivolts, and 10k ohm resistor would have 6.53 volts dropped across it. But then, if we take out that resistor, and in so doing, we put in a multimeter in place of it, so here's our trusty DMM. Put some leads from the DMM to the circuit. One thing that we have to understand about the DMM is it has an internal resistance of 10 million ohms. Ri, 10 meg ohms of resistance. And then that changes the characteristics of the circuit. Of course, you don't expect to measure any voltage drop across there because it's an open circuit. And this is what students have a lot of difficulty understanding. But now we've got a new circuit with 3.3k, 10 million ohms, and 10,000 ohms, which gives us a new equation to think about. I'll use a different colour for that. So 9 volts divided by the 3k3 plus the 10k plus the 10 meg ohms, that's going to be the new circuit current, and that's going to be equal to 899 nanoamps as compared to 653 microamps. So we're still going to have some current flowing in the circuit, but it's going to be extremely small amount of current. And then if we get that 899 nanoamps and we multiply it by each resistance, so let's just do that, 0.000000, we'll do it the long way, whoops, too many noughts, 899 nanoamps, which is 0.899 of 1 microamp times 3.3k resistor, 3300, equals, and we're only going to get 2.97 millivolts across here. 2.97 millivolts dropped across that resistor. And if we do the same calculation with that, get the 899 nanoamps, multiply it by 10 k ohms, we're going to get 8.99 millivolts developed across that resistor. The bulk of the 9 volts, then, if we think about Kirchhoff's voltage law, which says that the distribution of voltages around the circuit must add up to the applied voltage, Therefore, then 9 volts minus 2.97 millivolts minus 8.99 millivolts leaves us with almost 9 volts across this 10 million ohms of resistance. So let's call it 8.9 volts, which is going to be, for all intents and purposes, the full circuit voltage which has been applied. So it's a very important fact to understand this. If you do have an open circuit in a series circuit such as I've drawn on the board, and that is what we're working with today in our lab number 5, if we open circuit any of the resistors, the 10 million ohms is going to be so large compared to any of those that the current is going to be dramatically reduced and the bulk of the voltage dropped across the resistances is all going to be across that resistor. I hope that helps. I hope that makes more sense about that particular circuit and about open circuits in general.